Hello there, welcome to this video. This is 1A.2 and we're going to talk about rates of change and using rates of change within context as well as the interpretation of what that means. So without further ado, we're going to go ahead and talk about average rate of change. Average rate of change, very important in this course of AP Precalculus. It is just the ratio of change in your output values to the change in input values over a specified interval of the domain. And these problems always work this way. They're going to give you a domain. They're going to say given an interval, and here we see from x1 to x2, the average rate of change of f of x is, remember, your delta y over your delta x. So you may see in terms of y, but if you don't have these values, they give you a function. You can go ahead and plug in your interval. So you can plug in your x1, okay, and you can plug in your x2 to find those function values. And then we'll go ahead and calculate the change. So delta f of x is going to be f of x2 minus f of x1, your second y value minus your first y value, divided by your delta x, x2 minus x1. And again, your x values are always given in the specified interval. So a reminder, the average rate of change of a function for a given interval is equivalent to the slope of the line through the two endpoints of the interval. This is called a secant line. So if you ever see this word used, a secant line is referring to the slope of the line or the rate of change connecting 2 points. And here's a visual of this function, which is a quadratic function, f of x. And I have a point 2, 1 and 6, 9. So if I calculated the average rate of change, we rise 8 from 1 to 9, right? 9 minus 1, 8. And we run 4 from 2 to 6. So 6 minus 2 gives us an average rate of change of 2. That's the slope of that line that connects them. Now remember, a positive average rate of change tells us that the input values increase. The input values increase, the output values increase. And a negative average rate of change tells us that as the input values increase, the output value decreases. Essentially, a positive average rate of change means your function is going up. A negative rate of change means your function's going down. So let's go ahead and look at calculating average rate of change within context, and then looking at some interpretation and application. Example, the table gives the temperature for Baltimore, Maryland on July 5th, 2022, where x is the number of hours since midnight, x is equal to 0, and f of x is the temperature in degrees Fahrenheit. A, calculate the average rate of change in degrees Fahrenheit per hour from x equals 6 to x equals 9. When you're calculating average rate of change, you want to go ahead and find our function values. So note our interval starts at 6 and ends at 9. So f of 6, this is your x1. We're going to go ahead and use our table to find this information. So f of 6 is 78 degrees. So 6 hours after midnight, it was 78 degrees. Again, this is going to be your y1 or your f of x1. And then we can calculate f of 9. F of 9. So we'll go ahead and again use our table for this, and we get 79 degrees. Okay, so again, our average rate of change is going to be equal to delta f of x over delta x. Now for AP Precalculus, you always want to go ahead and set up a difference quotient. Difference quotient showing the difference in your outputs, which in this case is 79 minus 78, over the difference in your inputs, which is 9 minus 6. So we end up getting here 1 over 3, and this is degrees Fahrenheit per hour. Okay. So part B, one of the questions that you'll be asked on the AP exam is to interpret the average rate of change in part A in terms of the context. I always use an acronym called CUT to help me remember this. The C stands for context. They're asking you to interpret it, so you better talk about what it means in terms of context. So we're talking about the temperature in Baltimore, Maryland on July 5th, 2022. And so you're going to talk about the average rate of change. It is increasing. You want to use a directional word. So we're increasing at an average rate of 1/3. And the U in my CUT acronym stands for units. Always make sure you include the units. So here 1/3 degree Fahrenheit per hour. And then the T stands for time. This is not the average rate of change for the whole night. The temperature is not constantly increasing in 1/3 degree per hour. So you have to specify when this is applicable. So we're going to go ahead and say here from T equals, or sorry, not T, that's not the input variable here, it's X. X equals 6 to X equals 9 hours after midnight. If you wanted to say 6 a.m. to 9 a.m., you could go ahead and do that. But just note that these are the three things you'll want to include. You want to include, again, the context. So what are you talking about? We're talking about the temperature. You want to use a directional word here. It's increasing at that average rate. And you want to include units. So here's your units, and specify the time, which we did. You can switch these around as long as you have all three. You're good. Let's go ahead and look at question C. They say, use f of 6 and the average rate of change in part A to estimate the temperature when x is equal to 8. Okay, so they want us to go ahead, they're explicitly asking us to find what is f of 8. We want to estimate this. And they say, use f of 6. Now, I'm going to go ahead and use f of 6 because that gives me a starting location. I know that the temperature 6 hours after midnight is 78 degrees. So I have 78 degrees Fahrenheit. And then I'm going to use the average rate of change. We just found that the average rate of change from 6 to 9 was about 1/3 a degree per hour. So what I'm going to go ahead and do here is I'm going to add the average rate of change. I'm going to add the average rate of change. And I'm going to multiply times the amount of x values that I have to cover. So I'm starting at 6 and I want 8. So I'm going to take 8 minus 6. So essentially 2 more hours have to pass, right, in order to end up at 8 a.m. or 8 hours past midnight. So I'm going to add 1/3 degree Fahrenheit per hour times 2 hours. So I'm starting, I like to call this start plus problem. You'll see this in calculus too, but I'm starting here and then I'm going to use my average rate of change to estimate here. So this is going to be equal to 78 plus 2/3 of a degree Fahrenheit here. Okay. If you're wondering about units, our hours are going to cancel here, and I'm going to approximate this to 3 decimals. I'm going to say 78.667 degrees Fahrenheit. Okay. All right. So there's our temperature at 8. Example 2. So here we have the same exact context, except they want us to calculate the average rate of change in degrees Fahrenheit per hour from x equals 12 to x equals 17. Okay. I know my interval. Here's my x1, 12. My x2 is 17. So I'm going to find my function values. The function value at 12, this was going to be essentially noon, is 86 degrees Fahrenheit. And the temperature in Baltimore, 17 hours. If you're used to military time, we're just going to subtract 12. You get 5 p.m. That's going to be 78 degrees Fahrenheit. Okay, so in order to calculate the average rate of change, I'm going to set up my difference quotient, my second function value, 78 degrees Fahrenheit, minus 86 degrees Fahrenheit, my first function value, divided by the second x value, which was 17 17 minus 12. Okay, so this is going to give us, it looks like negative 8 degrees Fahrenheit over 5 hours. and approximated this is negative 1.6 degrees Fahrenheit per hour. That's our average rate of change. Okay, we're going to go ahead and interpret this. So again, I want you to remember cut. I want you to remember the context first. So we can say the temperature in Baltimore, Maryland on July 5th. That's what we're talking about. 2022 is, well, this average rate of change, if I'm interpreting it, it's negative. That means the temperature is going down. It is decreasing. I want to say decreasing. Decreasing at an average rate of 1.6 degrees Fahrenheit per hour. There's my units, okay, and then time. When? From, you could say x equals 12 to x equals 17 hours after midnight, or I could say from noon to 5 p.m. And there you have it. Okay, C. Again, the approximation question. Use f of 17 and the average rate of change in part A to estimate the temperature when x is equal to 20. So f of 20 is going to be approximately what f of 17 is. We're going to start there, and then we're going to add our average rate of change, and we're going to multiply by the time from 17. So that's 3 hours, right? 20 minus 17. Okay, so this is equal to, we're starting at 78 degrees, okay, again, and this time we're subtracting, so pay attention, your average rate of change is a negative 1.6, so minus 1.6 times 3, which gives us 78 minus 4.8, so we get 73.2 degrees Fahrenheit. That's it. Okay. I have a new context problem here for you. This problem is with regards to the 2008 race of Usain Bolt, in which he set a world record time running the 100-meter sprint, running 100 meters in 9.69 seconds. Whew! Here's the table indicating his time recorded every 10 meters. So this is distance. This is Usain Bolt's distance. That's what this context is. The context is a little funny here. That's his distance, okay, based upon his time. So please pause this example. I'll go ahead and show you the answers here in a second. All right, so hopefully you went ahead and tried this. For this problem, calculating average rate of change, the first thing you want to do is you want to calculate the function values. So what was his distance at 1.85 seconds? That was 10 meters. What was his distance at 4.65 meters? 4.65 seconds. This was 40 meters, okay? So our average rate of change is going to be delta f of x, so f of x2, which is 40, minus f of x1, which is 10, and this is in meters, over our time here. So 4.65 seconds minus 1.85, this is in seconds. Okay, so we get 30 meters per 2.8 seconds, okay, which rounded to 3 decimal places. Always 3 decimal places for AP, rounded or truncated. I like to tell my students round correctly. We get 10.714 meters per second. Okay, cooking. All right, B, we're going to interpret the average rate of change in terms of context. If you haven't done this, please pause, and then I'll go over the context here. Okay, so hopefully you use the acronym CUT. Again, what's the context that we're talking about here? Well, we're talking about Usain Bolt's distance is what we're talking about in this race, right? So we could say in the 2000, I'm going to slow my brain down. In the 2008 Olympic race, Usain Bolt's distance is, okay, so there's the context. We're talking about Usain Bolt's distance. It's increasing, is increasing about 10.714 meters per second. Meters per second. Okay, so there's my units. From when? From 1.85 seconds to 4.65 seconds. Okay, we have our context, Usain Bolt's distance. We have our units, the meters per second, and then the seconds. And we have our time, which is here. Okay. Oh, I don't know if I talked about this in the last example. Notice here, I said it's decreasing at an average rate of 1.6. I know it's a negative average rate of change, but I don't use a negative 1.6 here. I don't use the negative because I already said it's decreasing. That's already indicating direction. So you would just use the absolute value on a decreasing problem. Okay, lastly, C. Please try this. I want you to try C, and then I'll go over the problem here in a second. Okay, so they say use D of 0 and the average rate of change in part A to estimate Usain Bolt's distance at 6 seconds. So D of 6. That's going to be approximately, using D of 0, okay, plus his average rate of change, his AROC or his slope, okay, times the distance covered. So that's 6 minus 0. So that's going to be 0 plus 10.714 times 6, which this works out to be 64.284 meters. Okay, they have some extra here. It says compare your result to the table of values. Is this estimate accurate? So looking at this table of values here, so at 6 seconds, which is 6 seconds, which is about here. Did he run about 64 meters? This table would indicate he was short. He was short of that. Okay, so it's not exactly accurate. Okay, last portion of this lesson, pretty straightforward. We're going to go ahead and look at a graph and then estimate average rates of change. Here's a couple of things you need to keep in mind. If a function is increasing, the rate of change is positive. If a function is decreasing, the rate of change is negative. And then specifically at a maximum and a minimum, the rate of change is going to be 0. There's no change. If I got really close to this, the rate of change would be 0. Kind of like throwing a ball up in the air and then it holds still at the top. Now, keep in mind, for an increasing interval, the steeper the curve, the greater that rate of change will be. For an increasing interval, the steeper. However, if I have a decreasing interval, the steeper the curve actually means it's a smaller rate of change. And that's because it's a negative rate of change. So if it's more negative, that's going to be a lower value than another one. And we'll look at an example here. So let's go ahead and look at these examples here. It says the graph of the function y equals g of x is given. Place each set of points in least to greatest order using their rates of change. These problems, they love to give us a positive, a negative, and a 0 slope usually, or they'll make us determine which slope is more positive or more negative. So let's look. Example number 1, A, B, and C. So here's A, here's B, and here's C. So note, A is a negative slope, right? We're decreasing here. That's a negative slope. So that's some negative number. I don't know exactly. I could estimate, but I know it's negative. B, that's going up. That's going to be a positive slope. And then C, that is 0. That is 0. So here's the negative, positive, 0. So if I'm listing them in order, A is less than C, which is less than B. So A, C, B would be your order. Let's look at example 2. We have ACE. So AC, and instead of B, we now have E. So A is negative, and that's pretty steep. That's a pretty steep drop. C is again 0, and then E is also negative, but it's not as negative. So if I'm trying to attach a number to this, this would maybe be like a slope, I don't know, if I was estimating something like -5, right, dropping 5. So -5, and that's going to be the most steep. And then E here, we're really only dropping 1 on this interval. So A is less than E, which is less than C. Okay, so just kind of looking at a graph and estimating the rates of change. Please pause the video. I want you to try these 2 examples, and I'll show you the answers. Okay, hopefully you pause. Here is the solution for these ones. We have E, and then F, and then D. So E, then we have F, which is 0, and then D, which is a positive slope. So pretty straightforward. Practice problem 2, it is F, and then D, and then B. F, and then D, and then B. So F, 0. Then we have D, which is positive, maybe about a slope of 1. And then B, which is more steep. Okay? All right. Oh, battery's going to die. Got to plug in. Okay, last example here. And I know it says practice, but I want to have this one be an example. It says the table gives average rates of change of F over different intervals. Notice my X intervals here go from 0 to 1, 1 to 4, 4 to 8, 8 to 10, and they give us the average rate of change, which is your rise per 1 unit of run. So on this interval here, my function value actually grew 10. Okay? On the second interval, 1 to 4, that has a span of 3, and they're saying the average change over that is -3. Well, if I have 3 X values, and I'm changing on average a rate of -5, then that total change is going to be -15. For my next interval, I have a span of 4 and a rate of change of 2, giving us a total increase of 8. And then for our last interval, a span of 2, but an average rate of change of 6. So a total of 12 units of change. So which interval does the function have that increase the most? That's going to be D.
Pardon the interruption.
Pardon the interruption. All right, that's going to do it for this video on rates of change. Make sure you thumbs up. Give me some passive income. I'm trying to retire early. Subscribe for more awesome math content. Peace.